Hi, welcome back. This is Rakesh Naik. Today we are going to discuss about yet another application of dynamic programming. Today we are going to learn about optimal binary search tree. But before we start, a small information I'd like to share. In this channel we produce every video in 2 different languages. If you want to watch this video in Hindi, kindly follow the link given in the description. And if you have not yet subscribed, please subscribe and press the bell icon so that you will get regular updates from this channel. So, let's start. Before going to learn about what is optimal binary search tree, let us see what is a binary search tree. Basically, binary search tree or BST is a tree in which it follows some kind of conditions. It means in a binary tree, if the left node, if it is existing, is less than the parent and the right node is greater than the parent and all the left and right subnode are again a binary tree, then I'll say this is a binary search tree. For example, you can see here, if 10 is the parent or the root, to its left, whatever data we are having, all of them are less than 10. And whatever data to the right of it are greater than 10. Again, in the left subtree, 5 is the root. Again, in this, 3 is onto the left and 7 is onto the right. The same thing is there with the right subtree also. It means whatever subtree will take, the right node supposed to be greater than the root node and the left node supposed to be less than the root node. Let us say we are having 3 data, 10, 15 and 30. Then how many binary search tree we can have? We can have these many binary search tree. You can check the properties of binary search tree here. That roots right hand side data always be greater, left hand side data always be lesser. So we are getting 5 different binary search tree with 3 data in this. Now out of these 5 binary search tree, which binary search tree is optimal? Optimal means maximal or minimal, we can say based on some data. Here there is no data. Whenever we are talking about optimal binary search tree, we are talking about the searching time. So whenever we are talking about searching time, there is a probability associated with each data. For example, you can see the probability of searching 30 is, let us say, P2, probability of searching 10 is P1, probability of searching 35 is P3 and probability of searching 40 is P4. So then this tree I'll say the probability of successful search. Similarly, I can have probability of unsuccessful search. Let us say somebody wanted to find 5. Obviously, I'll start with 30. 5 is less than 30, so I'll move towards the left. I got 10. 5 is less than 10. Then I'll try to move towards its left. But the left node to 10 is a null pointer. So whatever rectangles I am getting here are all null pointers. And all the data are unsuccessful search. 5 I cannot search in these data. So it is an unsuccessful search. You can see when I am searching it, there are 4 data. I'll be having 4 successful search. But I'll be having 5 unsuccessful search. Means anything between 1 to 9 is the probability Q0. Anything between 11 to 30 is probability of Q1. Anything between 31 to 34 with probability Q2. Anything between 36 to 39 with probability Q3 and anything more than 40 of probability Q4. So these are the probability of unsuccessful search. Again repeating, if we are having n number of successful searches, then we'll be having n plus 1 number of unsuccessful searches. Now, let us take some data, 5 and 10. If I want to arrange it in the form of a binary search tree, I can take 5 as the root and 10 to its right child, or otherwise I'll take 10 as a root and 5 as its left child. Now let us assume the frequency of searching 5 is 3 and the frequency of searching 10 is 4. Here also the same data. Now, if I want to search 5, how many comparison or how many memory access I need? Of course, only one. So, the memory access for searching 5 is 1. But if I want to search 10, I need to compare with 5 and then I need to compare with 10. So, the memory access needed are 2. Similarly, here the memory access to search 10 is 4 and the memory access to search 5 is 2. Now let us try to find the cost of accessing 5. Now what is the frequency? 3. How many memory access you need? 1. So 3 into 1. Similarly, the cost of accessing 10. Frequency is 4 and memory access is 2. Multiplied, we got 8. So adding this to the total successful search becomes 11. Let us try to find it here. To access 10, we'll be having 4, that is 1 into 4. And to access 5, we'll be having 6. So the total cost we are getting is 10. Now you can see, by a simple arrangement with 2 data, I can say that this arrangement is better than this arrangement. Now I can say out of these two, this is an optimal tree, rather optimal binary search tree. With 2 data, with successful searches only, we found this. But somebody may have unsuccessful searches also. Let us try to take that. Already we have seen for successful search, the access I need is 11. But when I take unsuccessful search, let us say the frequency of searching between 1 to 4 is 2 and the left child is a null pointer. That's why I need 1 memory access. And anything between 1 to 4 is an unsuccessful search. Similarly, anything between 6 to 9 is an unsuccessful search. Let us say its frequency is 2. I need to come to 5, then to 10, and then I'll say it is a successful search or unsuccessful search. That's why memory access needed is 2. Similarly, anything greater than 10 also need 2 memory access. Let us assume that its frequency is 3. Then for all the unsuccessful searches, the cost will be 2 plus 4 plus 6, that is 12. Now in total we'll be having 23. Let us take the other tree. In this also we'll be having successful search as 10 and the cost of unsuccessful search is 4, 2 into 2, then 2 into 2, then 3 into 1. 4 plus 4 plus 3, that is 11. So the total cost including the successful search and unsuccessful search is 21. Now you can see this tree is an optimal binary search tree by taking both the successful search and unsuccessful search into consideration. Now you can see with 2 data I can calculate in this way. But if the data are more, then how to calculate it? We need to apply dynamic algorithm to find the optimal binary search tree. As I have already told you that we need a optimal binary search tree, and in that I want to arrange the nodes in level wise such that the total cost will be minimum. And with one observation I can see the most frequently accessed data will be at the top of the tree and the less frequently accessed data will be at the bottom of the tree. Now let us try to understand this with the help of an example. Let us say there are 4 data and the data are do, while, if and until. Okay. We'll be having 1, 2, 3 and 4th data. And the frequency of searching the first data is 3. That is, I'll be searching do as 3, while for 3, if 1 and until 1. So this is the frequency of searching. As there are 4 data for successful search, obviously there will be 5 data for unsuccessful search. So let the data be 2, 3, 1, 1, 1. So I can find the probability of successful search as 3 by 8, 3 by 8, 1 by 8, 1 by 8. And the probability of unsuccessful search as 2 by 8, 3 by 8, 1 by 8, 1 by 8 and 1 by 8. Now we are going to use these 3 formula in order to find the optimal binary search tree. How to use it? Don't worry, we are going to do it with this problem. The first thing we are going to do is we are going to assign some initial data. That is WII, RII and CII. The value to be QI 0 and 0. So QI values are what? 2, 3, 1, 1, 1. So W00 value is Q0 value, that is 2. W11 become 3. W22 become 1. W33 1. W44 1. Similarly, RII and CII value will be 0. So all this value becomes 0. For that we need to construct a table like this, and in this table we are going to fill the data one after another. So we got calculated this data, we filled it. Now the remaining data I need to fill by applying the formula 1, 2 and 3. But first we need to find all the Wij values, because we are going to use it for calculating Cij values. Now take j minus I equal to 1. I is 0, j is 1. So j minus I become 1. And the formula we are having is Wij equal to Pj plus Qj plus Wij minus 1. So it becomes P1, Q1 and W00. What is the value of P1? P1 value is 3. What is the value of Q1? Q1 value is also 3. And W00 value is 2. So 3 plus 3 plus 2 becomes 8. Similarly, all other values where j minus I equal to 1 we need to find. That is W12, W23, W34. And the values will be 7, 3 and 3 respectively. Now let us find j minus I equal to 2. It means I value is 0, j value is 2. Let us apply this formula again. P2 value is 3, Q2 value is 1 and W01 value is 8. So you are getting 3 plus 1 plus 8 is 12. So similarly, all other j minus I equal to 2 values we need to find. It means W13, W24. So the value of W13 will be 9 and the value for W24 will be 5. Next, j minus I equal to 3 you need to find. It means here I equal to 0, j equal to 3. So the same formula we are going to use. P3 value is 1, Q3 value is 1 and W02 value is 12. So the value becomes 14. Similarly, W14 we need to find. J minus I is 3. So the value is 11. Similarly, j minus I equal to 4 we need to find. The value will be for W04 and the value we'll get is 16. So half of the work we have done. Now we'll be applying formula 1 in formula 2 and 3. We need not find the value of Rij. The value of Rij will get it from the second formula itself. What is the value of k for which it is satisfying. Now let us apply j minus I equal to 1. It means C01. Minimum of 0 is less than k is less than equal to 1. It means for what value of k this inequality is satisfying. For k equal to 1 this inequality is satisfying. So apply in this particular formula. Cij equal to minimum of I is less than k less than equal to j. Cik minus 1 plus Ckj plus Wij. So here if we will apply C00 plus C11 plus W01. C00 value is 0, C11 value is 0 and W01 value is 8. Already we are having here. And this condition we found the value for k equal to 1. So R01 equal to 1 and the value of C01 is 8. Similarly, let us find C12. It means j minus I equal to 1. Now here also this inequality is satisfied for k equal to 2. And if we are putting the values for k equal to 2, the value will get is 7. For C23, here again j minus I is 1. And this inequality is satisfying for k equal to 3. So we will be getting the value 3 with k equal to 3. And the last one is C34, where k value is 4. So we are getting the value 3 with k equal to 4. Now substitute these values in the table. So the second row we fill the data. Now the next one is j minus I equal to 2. It means what? C0 2. Here j equal to 2, I equal to 0. Now this inequality will be satisfying for k equal to 1 and 2. So C01 plus C22. This is for k equal to 2, and C00 plus C12, it is for k equal to 1. And then we need to add W02 value. Now the value will be 8 plus 0 and 0 plus 7. Minimum of these two is 7, and it is true for k equal to 1. That is the second one. And the sum we got 90. Similarly, C13 value will be 12 for k equal to 2, and C24 value is 8 for k equal to either 3 or 4. Now substitute these data here. Now the next one is taking j minus I equal to 3. So we are taking C03 value. And this inequality will be satisfying for k equal to 3, k equal to 2 and k equal to 1. So when we are taking k equal to 3, this part will come into picture. When we are taking k equal to 2, this part. And when we are taking k equal to 1, this part will be coming into picture. And let us take the value. The minimum of these are 11. And the value we are getting 25 for k equal to 2. Similarly, C14 value. And this value we are going to calculate for k equal to 4, 3 and 2. And you can see here the minimum value is 8, that what you are getting for k equal to 2. So you fill the data again for j minus I equal to 4. It means C04 value. So here k value is supposed to satisfy for 4, then for 3, then for 2 and then for 1. So these are the data that we need to calculate. And the value that we are going to get is 25 plus 0, 19 plus 3, 8 plus 8 and 0 plus 19. Out of these, 8 plus 8, 16 is smaller for this part. That is k equal to 2. So k becomes 2. So R04 value is 2 and C04 value is 32. Now substitute it here. Now half of the work is over. Now the data we are having is this one. R04 is equal to 2. It means k equal to 2. So initially we will take with T04 with k equal to 2. And we are going to apply this particular formula, that Tij equal to Tik minus 1 and Tkj. Now here k is equal to 2. If we will substitute, we will get T04 equal to T01 and T24. So this data I am going to have two child, that is T01 and T24. Now let us try to construct for T01. Now T01 means R01 we need to locate in the table, and this is the table where R01 equal to 1. It means k is equal to 1. Apply this formula once more. It will become T01 equal to T00 and T11. So we are going to write to the left side 00 and to its right side 11. Now we are going to take T24. And T24 will get from R24, where we are taking the value to be 3. It means k equal to 3. Now apply the formula here. We are getting T24 will be T22 and T34. So we are going to have the left child of T24 as T22 and right child as T34. Now we are going to find the left and right child of T34. Now locate where is R34 in the table. R34 we are going to find it here, where R34 value is equal to 4. It means k value is 4. So we are going to apply this formula and you will find T34 will be T33 and T44. So we are going to get this data. We already seen that R00, R11, R22, R33, R44 values are 0. So these T00, T11, T22, T33, T44 values we are going to neglect it. So we will be getting this particular tree. Now you can see k equal to 1, k equal to 2, k equal to 3 and k equal to 4. So for these data, we can write do, while, if and until. If you remember the question, in the question we are having the first data as do, second data as while, third data as if, and fourth data as until. So based on the k value, I need to write the data here. So this is how we are going to have our optimal binary search tree with searching cost as 32. I hope you understood how to obtain optimal binary search tree by using dynamic programming. If you understood, give me a like and share among your friends. In our next video, we are going to talk about yet another application